Welcome to the next lecture of your STLD subject. The today concept is Universal Shift Register. Alright. So here the name itself it is saying that it will do the total shifting operation which is available in the universe. Okay, so coming to here, our universe is digital subject. In our digital subject we have total shifting operations, totally 5 to 6 operations. They are: first one, serial in, serial output configuration, that is serial in, serial out, and it should work with left and right shift operations also. That is, we have to do the bidirectional shift register operation. Serial input, serial output, left shift register, right shift register. It indicates bidirectional shift register. And serial input, parallel output configuration, parallel input, serial output configuration, parallel input, parallel out configuration. Total 4 configuration. In that, the first configuration, serial input, serial output, that is nothing but as bidirectional shift register. These are all the operations we have to do here. Okay, right. For doing this 4 operation, what are the input and output terminals we require for universal shift register? For serial, here we need serial inputs and serial outputs, and parallel inputs, parallel outputs, and we need left serial in data and right serial in data. Like that, we need some of the input and output terminals. Let us see those 4 input and output terminal for the universal shift register. So the first combination is shift left input data, shift right input data. These 2 terminals are required. Next, serial right shift output data, serial left shift output data. There is 2 output terminals which we have to take serially in the right direction and left direction. So first, for the serial input, serial output, left side and right side. Totally 4 signals here we have. 2 are the inputs, 2 are the outputs. Next, for giving the parallel data, we need 4 parallel inputs. They are D1, D2, D3. Okay, these are the parallel inputs. Next, we need 4 parallel outputs. They are Q1, Q2, Q3. These are the 4 parallel outputs. So totally 2 serial input data where left and right are available, where 2 serial out data left and right available, and 4 parallel in data and 4 parallel out data. Totally we need 10 terminals, 12 terminals, where 6 are the input terminals and 6 are the output terminals. So this is the universal shift register input and output configuration. Now, in the bidirectional shift register concept, we have discussed that when M is equal to 0, it acting as a left shift, when M is equal to 1, it acting as a right shift. But in this shift register, here we have to add 2 more operations, that is parallel input, parallel output, parallel input, serial output, serial input, parallel output. These operations also we have to add here. For that we need to take one more configuration, that is modes configuration of universal shift register. So this is the mode configuration of universal shift register. Here in the bidirectional shift register, we have mode control signal is only 1. Why? Because there we have 2 different type of operations. Here we have totally 4 different types of operations. For that we need 2 mode control signals. First one is S0 and second one is S1. Here we have one is S0 control signal and second one is S1 control signal. 2 control signals where S0, S1 is representing with 0, 0 configuration. If it is 0, 0, there is no change in the output. That is the previous output it should follows. Next, when you select the 0, 1 configuration, you have to enter the data in the shift right direction. So it should act as a shift right register. Next, coming to that 1, 0 configuration, when you selected S0, S1 values are 1, 0, then the shift right, the shift left data, that is you have to enter the data in the left side of the register. Next, the last combination, when S0, S1 values are 1, 1, you have to give the parallel inputs. So here I am giving the inputs serial right input, serial left input, that is parallel load input. So parallelly I am giving the data, serially from the left side I am giving the data, serially right side I am giving the data. So outputs, so there you have to represent the output terminals in which way you want to take, you can take. So you have to give the data entry pass in the shift to right direction, shift to left direction and parallel direction. So these are the 4 configuration. In the first configuration there is no change at the input and output terminal, so there is no change in the output. And 0, 1 configuration right serial right in data, and 1, 0 configuration left serial in data, and 1, 1 configuration parallel load data. Okay, right. Let us see 4:1 multiplexer operation for implementing this universal shift register. For implementing universal shift register, we have to know the 4 input multiplexer. So here S0, S1 signals I am taking as selection lines. Here I0, I1, I2, I3. I will discuss this what is this 4 inputs in the next slide. But we know that when the 0, 0 is selected here, the I0 is went to the output. Why? And when you select 0, 1, the I1 is went to the output. And when you select 1, 0, I2 is goes to output. When you select S1, S0 is equal to 1, 1, then I3 is went to the output Y signal. So this is the 4:1 multiplexer operation. 0, 0, when you select the output Y is equal to I0. 0, 1, if you select Y is equal to I1, 1, 0, Y is equal to I2, 1, 1, Y is equal to I3. These are the total 4 configurations of multiplexers. Okay, so in the previous mode we said that when you select 0, 0, there is no change in the shift register operation, and if you select 0, 1, right shift. When you select 1, 0, that is left shift, and when you select 1, 1, that is parallel load operation. Okay, for that we have taken this multiplexer. Right. Now, this is the universal shift register block diagram. This is a universal shift register block diagram. First, what is there in this block diagram? See here. First, 4:1 multiplexer. This is the 4:1 multiplexer. This is also 4:1 multiplexer, 4:1 multiplexer, 4:1 multiplexer. Totally here we have taken 4 4:1 multiplexers. Here we have taken 4 4:1 multiplexers. First, second, third, fourth. And coming to the inputs, 0, 1, 2, 3. That is, I have taken the down direction. These are the 4 inputs. Okay, these are the 4 inputs. These are the 4 inputs. These are the 4 inputs. Okay. So this red color represented structures are the inputs, and here I have given selection lines S0, S1. So all the multiplexers S0, S1 terminals I have shorted. So in this S1 here S1, S1, S1. All the S1s I shorted and I represented one S1 terminal, and all the S0 terminals I have shorted and I finally represented one S0 terminal. So for this 4 muxes, when I select here S0, S1 value 0, 0, and in all the muxes, the first 0 terminal is selected here. Okay, when you selected here 0, 1, the next second terminal, that is 1 represented terminal, will be selected here. Okay, you have to remember this one. So here 4:1 mux, here we have used. Next, these 4:1 mux outputs I connected to the D flip-flop. So this is the D flip-flop. So here this is the input to output configuration. So this is the mux output. This output I connected to the input of the D flip-flop here. In the same way, I connected the next flip-flop output to the D flip-flop input. So this is the output to the input configuration. That is the mux output I connected to the D flip-flop input. Okay, for the 4 muxes, I connected the 4 D flip-flops here. For the 4 muxes outputs, these 4 mux outputs I connected to the 4 D flip-flop inputs. This is very important. And here I am using a clear signal. When I have given the clear signal is equal to 0, all the flip-flop outputs are goes to 0. Whenever I giving the clear is equal to 1, now the clear is not working. So you can do your operations by enabling the clock signal or by giving the inputs. So that is the clear signal. Here I am taking the 4 parallel outputs from the here 4 outputs, that is A0, A1, A2, A3. Okay, otherwise if you want to take the output at A0, you can take. Otherwise, if you want to take the first flip-flop output A3, you can take here the output. So that is your choice. So outputs, how you are taking, that is up to you. But here we have to give the data, right? So when I said that previously, we have 4 combinations, that is 0, 0, 0, 0, no change. When you select the S0, S1 values are 0, 0, then there is no change at the output. When you select the 0, 1, then right shift, and when you select the 1, 0, that is left shift, and when you select the data, that is parallel operation. Parallel operation is we are going to perform. So first see the 0, 0 configuration, then see the 1, 1 configuration. So see here 0, 0. So when you select the S0, S1 value 0, 0, this 0 terminal, this 0 terminal, this 0 terminal, this 0 terminal is going to select here. So coming to see here, what is this 0 terminal? This 0 terminal, see here, I am drawing here this 0 terminal. This 0 terminal is connected to the same flip-flop, first flip-flop output. The first mux input 0 is connected to the first mux output. In the same way, see here. Okay, so the second mux, the second flip-flop output is connected to the second mux input, and in the same way, the third flip-flop output is connected to the third mux input, and the fourth flip-flop output is connected to the fourth mux input. Okay, so there is no change. The previous output followed here. Why? Because when you select 0, 0, the 0 terminal is shorted to the output. That is, whatever the information available at the 0, that information will be sent to the Y. So this Y terminal is connected to the D flip-flop input. So what the D flip-flop is doing here, so whatever the input is connected for the D flip-flop, the same input is followed to the output. It's very simple thing. This 0 terminal is directly connected to the D flip-flop. That is, the output of the flip-flop is connected to the same flip-flop input through the mux. Through the mux, the same input here we are connected. In the same way, all the D flip-flops are connected to their own output. It is connected. So when you select the S0, S1 values are 0, 0, then this operation is going to here. Next coming to that, 0, 1 configuration. So 1, 1 configuration we will see. 1, 1. So what is there at 1, 1? When you give the S0 value 1, S1 value 1, then the third, so this 3 pin is selected here. Okay, so see here, in all the flip-flops, the 3 pin is selected here. The 3 pin is selected here. When you are giving S1 value is equal to 1 and S0 value is equal to 1. So when you are giving the selection lines 1, 1, this third terminals are selected in this muxes. So this 3 pin representation, here it is I3, and this is I2, and this is I1, and this is I0. So here the 4 inputs are representing I0, I1, I2, I3. This is parallelly we are giving the data to the muxes. Parallelly we are giving the data to this muxes. That is, the output Y is directly connected to the I3. The output of Y is directly connected to the I2. The input of the D flip-flop is connected to the I1. The input of the D flip-flop of this one is connected to this I0. First flip-flop, second flip-flop, third flip-flop, fourth flip-flop. So the D input is connected to this I3. That is, parallelly I0, I1, I2, I3 data is entered into this 4 D flip-flops. The same output is presented at the output when you have given the clock signals. So this is about 1, 1 configuration. This is 1, 1 configuration. Now we have completed 0, 0 configuration and 1, 1 configuration. So 0, 0 configuration, the same output is connected to the flip-flop input through the mux. In the 1, 1 configuration, the parallel input is connected to the D flip-flop through the mux. So this is the 1, 1 configuration. Next coming to that 0, 1 configuration. Next 0, 1 configuration. In this 0, 1 configuration, shift right operation. That is, you have to give the data at the left side and this data is moving to the right side operation. So when you select the 0, 1 operation, so see here, when you select the 0, 1 operation, so see here, this is the 0, 1. Then this first terminal is going to select here. this first terminal is going to selected here. So see here, for the first terminal of this flip-flop, we are giving the data at the shift right operation. Okay, for the shift right operation, you are giving the data at left side. Okay, for doing the shift right operation. So this data enter into the D flip-flop through the mux with using terminal 1. Next, in the same way, the D flip-flop, the first D flip-flop output is connected to the second flip-flop first terminal. So see here, the first flip-flop output is connected to the second flip-flop first terminal. In the same way, the second flip-flop output is second flip-flop output is connected to the next flip-flop input in the place of 1. When you are selected 0, 1, all the 1 terminals are activated. That is, the output of this flip-flop is connected to the second flip-flop input. Next, this output is connected to the next flip-flop input through 1 terminal. Right? So through this 1 terminal, the output is connected to this flip-flop. So through this one, the output through the 1 terminal, the output is connected to this D flip-flop input. So in this way, we are shifting the data from left to right. Next, last combination, 1-0 combination. When you select the 1-0 combination, so the terminal 2 is selected here. This second terminal is activated here. Okay, so see here, at the last mux, at the second terminal, we are giving the data to move the data in the left sided direction. Okay, you are giving the data at the right side, but the data is moving to the left side. So here you are giving the data through the second terminal, and this data is connected to this last flip-flop output. That is, this D flip-flop output is again connected to the next D flip-flop second terminal. That is, the flip-flop output is connected through this terminal to the next flip-flop input. And in the same way, this flip-flop output is connected to the next flip-flop input to terminal 2 and this D flip-flop input. That is, the output of this flip-flop is connected to the next flip-flop input through the mux via 2 terminal, 1-0 terminal of the multiplexer. Next, the output of this one is connected to this next D flip-flop through this mux by using second terminal. Why? Because the second is shorted to this Y and this Y is connected to the D. And this is the final output. You can connect the output at the left shift register at the A3. At the A3, you can connect the output. At the place of the first mux input, you have to give the data. So this is the 1-0 configuration. Right. So this is about 4-bit universal shift register. In this 4-bit universal shift register, totally 00, 01, 10, 11. Totally 4 configuration modes are available. In the 00, there is no change in the outputs of the flip-flops. Why? Because the outputs are connected to the same flip-flop inputs through the 0 terminal. Next, in the configuration of when you selected 0, S2, S0 values are 1, 1. So in the 1, 1 configuration, the third terminal is selected and parallelly I0, I1, I2, I3 data is entered into the D flip-flops. The same output will be available at the output. That is the parallel load combination. Next, coming to that, when you select the 0-1 combination, the data entered in the left side towards the data is moving to the right side direction. When you are giving the 1-0 operation, the data entered from the right side and it is moving to the left sided direction. So it acting as a left shift operation. So this is the different types of configuration modes are available in the universal shift register. So you have to practice this diagram. Okay, I am erasing everything. Now draw this diagram and note down all the information. Okay, right. Thank you.